Namaskar friends, welcome to session 18 of our course on product design using value engineering. So currently we are in the fourth week of our discussion and we are left with 3 more sessions to complete the course. As you may have realized by now that this is a very exhaustive course and a very practical course. So practical, I mean to say that the concepts that we learn are directly applicable to what we see around us. The products that we see around us, there is always a scope for improvement, and if we follow the concepts of value engineering, we can easily modify the products in terms of their design, in terms of their functional requirements, in terms of the materials that we use to create those products, in terms of the manufacturing processes that we use to make those products. So basically there is a scope for improvement in each and every product that we see around us. Sometimes the manufacturing processes can be made more effective, more efficient, easier, as well as fast, quick, cost effective. So from manufacturing point of view, there are a lot of opportunities where we can improve our product. Similarly, from materials point of view also, we can make lot of changes in the materials that are being used and make the product functionally satisfying as well as at the same time cost effective. So we can see that from materials point of view, from manufacturing point of view, there is a scope where we can change the product. Similarly, from design point of view also, we can come up with alternate designs. We can try to combine few assembly operations. Suppose the product has to be assembled, we can see that how many assembly operations are being done. Can we combine few parts? Can we modularize some of the parts so that the assembly operation, number of assembly operations can be reduced? So basically we can say that our target is to make our product functionally satisfying and at the same time it must be cost effective. So it is a very practical oriented course, and today we are going to take a case study and try to understand that how the value engineering concepts that we have learned can be applied. So the approach is known to all of you. All of you are aware that how to solve any value engineering case or how to solve any problem using the concepts, principles, rules, guidelines of value engineering. Today we will see a practical application, a case study where successfully value engineering has been applied and lot of financial benefits, lot of cost benefits have been achieved. So this case study that we are going to take today has been taken from a very you can say practical oriented book on value engineering, a practical approach for owners, designers and contractors. The book has been written by Mr. Larry Zimmerman and Glendy Hart. This is a good book. So you can see it is a practical approach. So basically we can apply the principles that we are learning to solve our product design problems. So let us see what is this case study. This case study is related to the design modifications in the wastewater treatment facility. So let us, as the saying goes, that first and foremost we must try to achieve or attain or collect all possible information related to the problem at hand or the design that we are going to modify or the product which we are going to analyze. So let us see what is the information given in the book related to this wastewater treatment facility. So this wastewater treatment facility is located in the Oklahoma City. So this is the facility serves several municipalities surrounding the city. So there is Oklahoma City and around the city there are number of municipalities, and this central facility, wastewater treatment facility, is serving all these municipalities. So in 1975 the estimated population of the service area was 3,91,000 people, and an increase in that increased to 5,03,000 by the year 2000. That is the forecast. So the current population is given and it may increase to this population by the year 2000, and the facility we are talking of, time domain is from 1975 to 2000. So the facility has to be revamped, the facility must be upgraded, the facility must be expanded, so that this number of people who are residing in those areas is going to increase. Therefore, the load on this wastewater treatment facility is also going to increase. The proposed facility, when complete, will provide sewage treatment services to the area until the year 2000. So, till 2000 it is expected that the facility which is being created, this wastewater facility, will serve the society till 2000. Then later on, maybe it may be further upgraded and revamped, or maybe modified as per the requirement. So, at which time after 2000 additional treatment facility may be needed. So, after 2000 there may be requirement for a additional treatment facility, which means that while we are designing this facility, while we are analyzing this facility, we must take into account that the population is further going to increase, and there may be a requirement for upgradation or expansion of the existing facility. So, with those we can say constraints, the designers achieved or attacked this problem. So, what are the requirements now? First thing is the information, what is the facility, what is the load on this facility in terms of the population, what is the time domain for which the facility is expected to serve the community, the number of municipalities that are being served by the community, by this facility, sorry. So, all this information is already now available with us. Now, we can see what are the project requirements. The primary parameters in the design of the wastewater facility are, so these are the parameters for design: the size of the plant, that is maybe the first parameter, and the degree of treatment necessary to meet the discharge requirements. Now, whatever wastewater is suppose coming, it has to be treated and then it has to be discharged maybe into a river. So, what are the degree of treatment or what are the discharge requirements, because each and every country will have certain discharge requirements in terms of the type of effluents that, or the type of, we can say, bacteria or the type of other pollutants that are there in the water, how to treat them and at what level they can be discharged into the, or what type of treatment and what level of treatment or what degree of treatment is necessary to ensure that the water is now treated to be discharged into the flowing river. So, two things are very important: the size of the plant and the degree of treatment necessary. The treatment capacity requirements are established during the planning stage. So, that has to be taken into account. What is the type of treatment and the degree of treatment that is necessary in order to follow the government guidelines. So, the effluent limitations are set by the State Department of Health. So, what type of effluents we can discharge into the stream, these limitations are set by the Department of Health based on the assimilation characteristics of the receiving stream. So, receiving stream where we are discharging our treated wastewater and other health factors. So, depending upon that, what are the state guidelines for ensuring the dumping or the discharge of the treated water into the flowing stream, we have to see that how our treatment facility must operate. What are the process parameters for operating our wastewater treatment facility, so that the discharge that we are putting into the stream is acceptable as per the government norms. So, this is the project requirement. Now, we can see this is the level of accepted limitations as set by the government. So, biochemical oxygen demands, this is 30-day average value is given, 7-day average. Similarly, we can see fecal coliform bacteria number per 100 ml. So, this number has to be satisfied, 30-day average has to be this and 7-day average has to be this. So, pH limits is also important, 6 to 9, 6 to 9. So, 30-day average values are given, 7-day average values are given. So, these are the constraints which have to be taken care of while we are designing our facility. So, based on this, suspended solids also you see. So, there can be other criteria also, which are the effluent limitations. So, this is the, you can say, requirement which the plant has to meet. So, if the plant is not able to get to this level of, you can say, limitations or this level of criteria, the treatment will be ineffective and the government may not allow the effluents to be discharged into the stream. So, this criteria has to be met. Now, this is the description of the project. The unit operations required for the treatment are, so what are the requirements? We can see here, there is a liquid stream and there is a sludge handling stream. So, this is star is for ultimate capacity of the plant and double star is for the average flow that is required. So, we can see the liquid stream, what are the important units there? Influent pumping, screening, grit removal, primary clarification, activated sludge unit, recycle pumping, final clarification and chlorination. Similarly, in sludge handling, primary sludge pumping, activated sludge pumping. So, all these are the units. So, as we have seen in value engineering that whenever we attack a problem, we use the technique of, now since you know all the techniques, blast, create and refine. So, what is our target? We try to blast the complete product or the complete facility or the complete service into its individual components or parts or sub assemblies, and then we try to see each and every sub assembly, that what is the basic function and the secondary function of this sub assembly, and then we try to create, we try to generate, we try to brainstorm and we try to find out a large number of alternatives which can solve the similar function, but at a reasonable cost or at a even at a higher cost, but at a lower overall life cycle cost. So, based on that we try to select the best alternatives so that the functional requirements are met. So, in that line only this complete, we can say, classification is into the individual units like chemical conditioning, incineration, which is another synonym for burning. So, we have different types of units which make up this wastewater treatment facility. Now, we can focus on each of these units independently, individually, and then try to find out that what are the basic and the secondary functions for these units. So, I will suggest that some of the terms here may not be that relevant to all the learners. So, the important point to understand here is that what is the step by step procedure that we can follow to solve any actual problem. So, the actual problem here is that we have to find out a cost effective design so that our overall cost is minimized. So, let us now try to see the next stage, that is who is going to do the value engineering. Now, the project, we have a project at hand, we know this is the project that has to be solved. These are the project requirements. This is the level of effluent treatment that is necessary. Then what is the degree of effluent treatment necessary? Then what are the units that are there in a standard effluent treatment plant or wastewater treatment plant? Now, based on these units, the teams have to be made. As we have seen in the techniques of value engineering, use the expertise, knowledge of the specialists. That is one technique. Use the specialist knowledge of the vendors. So, when you are brainstorming or creative idea generation is going on, we must take into account the expertise of the people who can help us to solve this problem. So, the teams are established. What is the purpose of the teams? The teams are established to ensure the adequate time and talent to analyze all aspects of the project. So, timely manner the project has to be completed and the talent has to be harnessed or used. So, we can see team 1 is made up of a certified value specialist. So, very special companies have this guts to have a value specialist. So, the companies which want to be successful normally like to have a value specialist. So, we have in this case study there is a certified value specialist which is available with the company, or they can be hired as consultants also. Then there is a sanitary engineer, civil engineer, landscape architect and structural engineer. This is team 1. So, this study A is the conceptual design of the plant or of the facility. Similarly, there is a team 2, again there is a certified value and specialist, sanitary engineer, chemical engineer, electrical engineer, cost and construction owners representative. So, there are, you can see, team 1 and team 2 which is selected to solve this problem. Then study B is the design. So, first is the conceptual design. So, conceptual design is done by team 1 and team 2, and then the design and development, that is study B, that is done by certified value analyst, again mechanical engineer, sanitary engineer, cost construction owners representative. Similarly, structural engineer, electrical engineer, civil engineer, architect and mechanical engineer, that is team 2. So, this is the constitution of the teams that has been made to solve or to design this plant facility. We can see that there are specialists drawn from different areas of expertise. So, there are mechanical engineers, electrical engineers, chemical engineers, sanitary engineers, value specialists, representatives from the construction company. So, this is a diverse group of individuals who will sit, brainstorm and find out creative solutions to save a lot of money for the institute or for the government or for the organization which is going to develop this facility. Now, we have a team, we have a problem at hand, we have the limitation and the constraints that we have to follow. Now, finally, we do the functional analysis. Now, what are the various units that we have already seen in the wastewater treatment facility? So, there is a influent pump station, screening is done, flow measurement, grit removal, pre-aeration, primary clarifiers, aeration basins and equipment, chlorination, instrumentation, site work. So, there are a lot of, you can say, steps or elements that make up this wastewater treatment facility. Now, as we know, we do the functional analysis, we try to define the function using the verb and a noun. So, this verb and a noun technique is used. So, in verb and a noun, what is the influent pump station? What is the function? Lifts sewage. Similarly, suppose we say primary clarifiers, what is the function? Remove solids. Now, again the kind of function, it is given here, the kind of function can be either basic or it can be secondary. So, the kind of function is also mentioned, influent pump station lifts sewage, that is the secondary function for this. Similarly, primary clarifiers remove solid, this is the basic function for this facility, and the wherever possible the cost is also written. So, we have a cost component also. Similarly, we can see action verb and measurable noun are put here. So, we can also calculate the cost to worth ratio. So, this is a worth also is something which is mentioned. So, worth and cost, sometimes it may be so possible that we are spending some money, but not adding any value to the facility or not creating any value for the facility. So, in that case the worth may be less. So, here also screening, you see the remove trash, cost is given, similarly worth is also given, that currently we are spending 1250 units of money, but it can be done in 1000 also. So, we can calculate cost by worth ratio. So, this is the basic functional analysis for the different units which we are going to use for our wastewater treatment facility. So, functional analysis of the treatment plant identified the required elements. So, these are all the elements which are given in this column and the associated cost. So, the costs are also given. The team analyzed the entire plant where the basic function was to treat the sewage. Now, the basic purpose is known to all of us, it is a sewage treatment facility. Now, we can see here again this is primary sludge pumping station, it is I think in continuation. So, we have verb and noun pump sludge, it is a secondary function, the cost is this much, worth is this much. So, very easily we can calculate the total cost to worth ratio and cost to worth for the basic functions that have to be achieved. So, here we have seen that there are opportunities where we can make the modification, because the cost is on the higher side, the worth is on the lower side. So therefore we can see that if we put efforts in these particular subsections or sub elements of the overall sludge or the waste treatment facility, we can very easily reduce the gap between the cost and the worth. Now the next stage, as we know that now we know that this is the overall facility, these are the individual elements or the parts or the subsystems which create or which are responsible for our basic function of treating the sludge or the waste. So we have now created a functional analysis matrix or functional analysis table, in which we know what is the role or what in engineering terms what is the function of each and every facility. What is the cost of that facility? Facility, here I mean to say, is the element or the part, that this is the part, maybe this pump, this is the basic function, this is for the basic function, this is the cost. So after that now we can see that there are opportunities where there is a difference between cost and the worth. So why not to attack those problems? Or there are many units, many elements in the overall system which are only serving the secondary function, are not contributing anything towards the basic function of treatment of sewage. So now we have found out that yes, there exist a large number of opportunities which can be tapped, which can be exploited for better cost justification of the project. So the team, there is a team already, we know there is a conceptual design team and there is a actual equipment design team. So the team judged each idea for its technical merit and potential for acceptance. The ideas were rated from 1 to 10 following the criteria. So the now creative and judgment phase, number of ideas were created. So if we go to the next slide, we can see there are large number of creative ideas which were generated, and they are listed here one by one, and the advantage of each idea and the disadvantage of each idea is also given, and the rating to each and every idea is given. So we can see the scale is from 1 to 10 for the ideas. 10 means most desirable and 1 means least desirable. So we can see that there are number of ideas which were generated. Like one of the ideas I will read for you: use the screw pumps for return sludge pumps. So we can, this is one idea, that for return sludge pumps we can use screw pumps also. Then there is another idea, maybe I will read, for reduce the size of the pre-aeration tanks. So it will lead to energy savings, that is advantage, but there is no disadvantage for this idea. Similarly, we can say reduce freeboard, lower roof of the grit building. So advantage is initial cost will be less. So we can see there are large number of ideas which were created. So if we go back and see, the team judged each idea for its technical merit and potential for acceptance. The ideas were rated from 1 to 10, as we have seen, 1 to 10, using the following criteria. What is the criteria? What is the potential of the idea towards cost saving? What is the validity of the idea? Sometimes some of the ideas that we create may not be technically feasible or commercially viable. Third is whether it is leading to improvement of the design. Then what will be the cost of redesign? Sometimes it happens that we have a very brilliant idea, but it challenges the very basic aspect of design, and there is a lot of cost involved for redesigning. So that also is a criteria to decide which idea is going to be feasible for us. And the other criteria is likelihood of acceptance, because sometimes there may be a cultural mind block also, and sometimes there is a societal implications also. Technically 5 ideas may be feasible, but maybe because of our cultural thought process or because of our societal way, the way we think as a community, the idea may be selected. So there is a likelihood of acceptance also based on all the constraints as well as the criteria. Now based on all these criteria, these ideas were scrutinized and ranking was given from 1 to 10, and finally the best ideas were selected for further implementation. So, the development, once we have seen that there are number of ideas. So, this is a glimpse of the ideas. So, we can see that a total of 33 ideas were carried forward to the development phase. So, 33 ideas. Now, today we are trying to take two examples of recommendations that were implemented by the designer. So, today we are going to talk about two examples only, but there were 33 ideas which were generated by the conceptual design team. Findings of a study revealed that potential for significant savings on initial cost as well as life cycle cost of the plant. So, whatever ideas were generated, they had the potential of savings not only on the initial cost, but also on the life cycle cost of the plant. So, we are quickly going to see the two ideas. So, this is the development and the recommendation phase. So, we are showing you the template also, how the normally templates look like when we are going to report or document any value engineering case study. So, we have seen that right from the identification of the problem, then collecting all the information related to the problem, then forming a team which is going to solve the problem, establishing the constraints and the design requirements, finally doing the functional analysis for each and every component of the design. Then the functional cost analysis, cost and worth ratio can be calculated. Then we have to create a large number of ideas to focus on the functional requirements of the project or the plant or the product, and finally we select some best ideas based on a criteria, as we have seen in this case study. Once the ideas are generated and they have been scrutinized based on certain criteria, we go to the next stage of development and recommendation. So, here we are quickly going to take two ideas. So, this is idea number 1 that we are going to discuss today. So, the item is eliminate the outfall line. Original concept. What was the original concept? The original outfall from the chlorine contact basin is contained in a 72-inch diameter RCP pipeline before discharging it into the open channel. So, open channel. So, this is our existing system. What is our proposed system? The proposed change is, we will see in the diagram also, it is proposed that the length of the enclosed pipe be reduced and 450 linear feet of open channel be constructed in its place. So, let us now try to see the diagram. This is the diagram. So, this is a 72-inch RCP, this one RCP pipe, and the discharge is taking place here. This is the existing design, but once we propose a change, so this is from basin. So, this type of design is now modified to a straight design, and here it is being discharged. So, this RCP 72-inch RCP is not required now. So, we can see here the proposed change is, it is proposed that the length of the enclosed pipe, what is there? The original outfall from the chlorine contact basin is contained in a 72 diameter RCP pipeline. So, they say that it is proposed the length of the enclosed pipe be reduced and 450 linear feet of open channel be constructed in its place. So, this is a change in the design which is helping us to achieve a cost benefit. Now, what is the cost benefit that we can see? The proposed channel alignment can be aligned to reserve space for future plant additions also. Reduction of the initial cost of this proposal is a definite advantage. So, these are the advantages. So, initial cost you see, original design where RCP is used 70,000 and the proposed is only 2,000. So, savings you can say 68,000 only in one single unit of the overall sewage treatment plant. So, the annual cost, that is life cycle cost also, original is 6,420 and proposed is only 185, savings you can see 6,235. So, you can yourself see the savings are substantial. Therefore, a slight modification in the design without affecting the functional requirement of the flow is able to save us a lot of money. Similarly, we can take the other concept also. So, here we can see what is the original concept. The original concept is, the original design uses 3 54-inch diameter return sludge pumps, each with a capacity of 7,000 gallons per month. So, the original design 54-inch diameter return sludge pumps. So, these are the units which are being used and this is the capacity. The pumped flow is conveyed by a channel to the front of the aeration tanks and mixed with the influent sewage. The design concept is for a completely securate return sludge pump station for 20 mgd, that is another capacity unit, expansion to the treatment plant. So, this is another expansion that is possible. At an ultimate capacity of 80 mgd, 4 pump stations would be used to return the sludge. So, 80 mgd is million gallons per day. So, this is the, you can say, capacity. Now, this is the original concept. So, I think little bit detailed, but as I have told you in the very beginning that you may not be able to understand each and every term of this case study, but the approach is important, that how to approach a problem. Now, here in this case study, this is a sewage treatment case study. So, there will be use of lot of pumps, lot of channels through which the sewage will flow. So, we have to focus on these basic elements of pumps and the flow channels, and we have to optimize, redesign them so that we can save some money. One of the case study already you have seen related to the chlorination tank and the discharge, and change in the design has saved a lot of money. Similarly, here also with proposed concept we can save a lot of money. So, what is the proposed change? As we have seen, there can be some modification in the capacity that we are handling, some modification in the expansion capacity that we can handle at a later stage. So, some planning can help us save a lot of money. So, now what is the proposed change? They say design the pump station for a 40 mgd anticipating the next 20 mgd expansion. So, right now the we can say it is 80, focus is on 80, but it is suggested that you go for a 40 mgd anticipating the next 20 mgd expansion. 372-inch screw pumps designed for 16,000 gallons per month each. 2 pumps would be installed now and 1 in the future. 1 in the future means we are focusing on our planning aspect also, we are planning for the future, and here also instead of original concept we are modifying this figure as 40 mgd. Although some additional funds may be required during this phase, the total capital cost will be less. The operation of the aeration basin will be more uniform within a common mix and influent to each basin. It will also be more convenient to operate one station rather than the 2. So, instead of in place of 2 stations we are now focusing on 1 station only. So, I think I may not have been able to clear the concept very you can say clearly, but the point is very clear, that is how to solve any problem. This is related to civil engineering or mechanical engineering, design of a sewage treatment plant before the discharge is put into the flowing stream. So, here we can see there is a large number of units which are combining to form a system which is acting as a sewage treatment plant. So, here the reference is given in the very first slide. I suggest all the learners, if possible, if the book is available in the library for all of you, you can focus on the detailed study, because within a half an hour duration we will not be able to complete the study. The idea is to give you a reference that such type of successful applications of value engineering are possible, have been documented, and learners can take advantage of these documented case studies and try to frame a thought process that if they apply the concepts, principles, rules, guidelines, tools, techniques of value engineering, a lot of money can be saved for the organization. So, here we have seen 2 such cases. In first case there was a design modification, in second case there was a management application of doing something now, planning something for the future, and then trying to save money for the organization by better planning of the our facility. So, with this we conclude the today's session. In next session we will also take another successful implementation of value engineering, which will be discussed in the form of a case study. Thank you.